presentation today on turn insulation aging of motors exposed to fast pulses of inverter drive will be divided as follows. First, after a brief introduction, I will describe the differences between AC voltage and pulse width modulated or PWM voltages. We'll see how will the insulation be stressed in both of those cases, and I will describe how the characteristic change of the insulation can be characterized. I will describe the specimen used for the aging and the aging protocol. I will then present the result and conclude my presentation. It is well known that the stresses that the insulation will face with regard to PWM operation is completely different than the stresses resulting from AC voltage. At present, there is no well-documented study of the effect, the long-term effect of pulse operation on motor insulation. Some research teams are studying presently the effect of partial discharge degradation on the insulation of the motors, and we know that those partial discharge will occur when the fast pulses will cause large overvoltage on the insulation because of the impedance mismatch between the drive and the motor. In this particular study, we're mostly interested in what goes on below the inception voltage of the discharges. So what we're interested in finding out is a diagnostic tool that will allow us to look at the changes and quantify those changes resulting from PWM operation. If we have a look at the pulses that are generated by pulse width modulated drivers, we'll have one fundamental waveform that's typically of 60 Hz or less, and the fundamental waveform will be reproduced by a series of fast pulses, each of which will have a duration of tens of microseconds, and at the beginning and the end of each of the pulses, you'll get some oscillation lasting from 5 to 10 microseconds. Here we can see on the middle curve that a single pulse have a duration of 35 microseconds, but also on the bottom curve an overvoltage of 825 volts. For a nominal operation of 575 volt, this is a large overvoltage, but sometimes you can get overvoltage that are as large as 1.2 kV. In those cases, you would be, or you could be well above the discharge inception voltage, and you would damage the insulation with partial discharge activity. But again, in this presentation, we're only concerned of what goes on below the inception voltage. Because of the inductive nature of the motor winding, fast pulse that will enter the winding will cause some very large overshoot, and most of the voltage will appear across the few first turn of the insulation. There are two cases we want to consider separately. There's the preformed coils with an insulation type that's consisting of a ground wall insulation composed of epoxy and mica. The turn insulation also composed of epoxy and mica, and you also have insulated copper strand. For the lower voltage application, typically below 1 kilovolt, you would have random wound coils. In that type of coil, you would get individual strands that are insulated, impregnated with resin, and the coil itself would be encapsulated in an insulating sleeve. For pulse rise time of 1 microseconds or less, you will get very large overvoltage, and as much as 80% of the full phase voltage could appear between the two first turn of the winding. In that case, even if the random wound coils are of lower voltage than the preformed coil application, the voltage stresses between two different turns could be much larger. And this will give rise to pulses that we have tried to simulate with laboratory experimental drive, an electronic circuit that would give the pulses as you can see them here on the upper left corner. If we only look at the pink curve, you see that we had a nominal voltage of 600 volt, and this point was measured without any cable nor specimen connected to the drive. If we connect a 50 feet cable with a specimen at the other end, you will get an oscillation that's I'm going to give you the pulse that's appearing on the upper right corner. Again, only look at the pink curve, and you can see that you have the fast oscillation typical of what is resulting from PWM operation when there's an impedance mismatch. Now, the measurement point for this particular curve is the same than the previous one. If we now move the measurement point to the between the specimen and the cable, you will get again the oscillation. I would like you to notice that the time scale and magnitude scale on the bottom curve is not the same, but the typical duration of the pulse here is of 2 microseconds. The rise time is 120 nanoseconds, and the maximum voltage reached by the overvoltage pulse is 920 volts. Those pulses were used to age our specimens, and we used a repetition rate of 10 kilohertz. The type of specimen we use is shown in the next figure. It's a layer-to-layer type. It consists of 2 wires, one on top of each other over an insulating rod. One of the wires connected to the high voltage side of the specimen, and both ends of the other wire are connected to the ground of the drive. This type of specimen was not impregnated with any resin, and the material, the insulating material, was an imide coat, which is a 200 C class insulation. The thickness of the insulation was 25 micron, and this capacitance type specimen at a capacity of roughly 120 picofarad. The number of specimens that we've used is 4. 2 of them were used for electrical and thermal aging. The 2 other specimens were used as reference and did not see any electrical pulses. They only saw thermal aging. The diagnostic tools that were used, or diagnostic technique to try to quantify if there's change in the insulation, are capacitance and tan delta measurement that were performed at both 10 hertz and 1 kilohertz. We also did relaxation currents measurement and return voltage measurement. And finally, we did thermostimulated current measurement. All of those diagnostics were performed periodically during the aging of all of the 4 specimens. In the bottom figure, you can see the 3-step process that we have used to do the thermostimulated current. First, we have decreased the temperature from room temperature down to minus 50 degrees Celsius without any voltage applied. The temperature was then increased to a maximum of 150 degrees Celsius, during which time we measured the releasing of the charge, giving rise to a depolarization current. During step 2, we again decreased the temperature to its minimum value, to thereafter increasing it to 150 degrees C with a voltage applied of 50 volts. During that time, we did charge the specimen. All the empty strap were filled up. This gave rise to a polarization current that we measured. And finally, during step 3, we reduced the temperature again, removed the voltage, and on the last temperature ramp, we measured the depolarization current caused by the release of the charges. All of the result of the 3 different steps of the thermostimulated current measurement gave similar results. So what I'll be presenting in the following only regards the last step, step number 3. We'll now have a look in the table of the testing and aging of the different specimens. You can see that all of the 4 specimens that we used were measured with tan delta and capacitance measurement. We also used a relaxation current and return voltage measurement on all of those 4 specimens. But for Tsc measurement, we only measured the values or the current associated to specimen number 1 and 2. And the reason for this is because of the temperature excursion that are used during the Tsc measurement that went up to 150 degrees C. We were concerned that those temperatures may cause some changes in the insulation that is much greater, that would be much greater than the electrical aging itself. So we used the 4 first type of measurement to see if there was any difference between specimen number 3, 4, number 1 and 2. It turned out that all of the specimen changed or evolved the same way, so Tsc measurement did not cause any major change compared to the pulse aging. The type of aging that was used, we can see that specimen number 1 and 3 were aged under electrical pulses during phase 1, which is initial time to 1300 hours. This is best described on the bottom curve. You can see that at room temperature, we had a aging process that was going on that was only electrical on specimen number 1 and 3, and specimen number 2 and 4 that were used as reference were not aged electrically during that time. During phase 2, specimen number 1 and 3 again were aged electrically, but now we turned up the temperature, so we would increase the temperature up to 120 degrees Celsius, reduce it again to 50 degrees Celsius, and back up to 120 degrees Celsius. During that time, there was both electrical and thermal aging of specimen number 1 and 3, and again, specimen number 2 and 4 during that time were only aged thermally, no electrical pulses. What is presented in the proceeding only reflects the values stopping at the end of phase 2, but since then we have aged the specimen up to 2,700 hours, and we have aged during phase 3 at 120 degrees C and phase 4 at 50 degrees Celsius. The result from the 10 delta capacitance, relaxation current, and return voltage measurement showed some very large fluctuation during the aging time, but none of those changes could be attributed or correlated with the type of specimen or the type of aging, nor the total exposure time. On the contrary, if we looked at the result from the Tsc measurement, we have the following. The upper graph shows the result from specimen number 1 that was aged electrically and thermally. The bottom graph shows the result of specimen number 2 that was only aged thermally. For the first 6 curve on the upper graph, this represents the aging that took place, the electrical aging that took place during the first phase of the aging. You can see that all of the curves are perfectly superimposed. When the temperature was increased to 120 degrees C at the onset of phase 2, there was a slight difference in the current measured during the Tsc measurement, but there is hardly any change that could be observed from the previous curves. When the temperature was decreased to 50 degrees Celsius for the aging and pulse action was still on the specimen, the resulting current measured with Tsc analysis showed that the black and the blue curve showed quite a different current resulting from the detrapping of charge. So this indicates that there are some significant change occurring in the material even below the discharge inception voltage. Those changes are probably related to trapping and detrapping of charges. After the 50 degrees Celsius aging of this specimen, we increased back the voltage, or the temperature should I say, to 120 degrees C, and the resulting current measured after that aging step with Tsc, we measured that the current had lowered down to an intermediate value compared to the 2 previous curves and everything that was measured before. This will indicate that there are some changes that are occurring in the material, but after only short exposure time, it does not appear that those changes are permanent. If you compare those results with the result of the bottom curve for specimen number 2, you see that after even phase 1 or phase 2, there was absolutely no changes in the current measured by the Tsc technique. Those results only include the measurement that were made during phase 1 and phase 2 of the aging. Everything that was made during phase 3 and phase 4 are not presented here, but for specimen 2 there wasn't any changes or hardly any changes measured by Tsc. for the specimen number 1 that was age. All of the curves that we did measure were intermediate between the two last curves that I presented. In conclusion, I would like to say that the thermostimulated current measurement have shown that the combined effect of fast pulses and the higher temperature cause structural changes to the motor turn insulation. And we noted that the temperature alone was not sufficient to show any changes, as we saw with specimen number 2, and the electrical pulses alone were not sufficient either, as we saw during phase 1 with specimen number 1. We needed the combination of both temperature and electrical pulses to provoke any changes in the insulation of the motor. The relationship between the pulse sequence, the temperature, and the measured changes is still not clear and appears to be very complex. But one of our main goals was to identify a diagnostic tool that could be used to monitor or measure if there was any changes in the insulation property resulting from the fast pulse operation. The Tsc measurement has been identified as the best tool amongst the one we've used, and this is going to be important in the next phase of our project, where multiple specimens will be aged at different voltage level with or without pulse reversal and at different temperature to determine what are the most critical operating conditions. Thank you.